There are many different ways of expressing solution concentration. We've got a couple of qualitative descriptions and then a whole bunch of quantitative. Qualitative would be dilute versus concentrated. These are just relative terms. Dilute means small quantities of solute, concentrated means large quantities of solute, relative to the amount of solvent. Here is a table summarizing some of the different quantitative, and we're going to talk about each of these, but you might find this table helpful to refer to. So molarity, we talked about molarity back in section 4.4. Molarity is the amount of solute in moles divided by the volume of the solution in liters. That's the whole solution. One of the disadvantages of molarity is that it changes a little bit with temperature because volume changes slightly with temperature for liquids. And so if you have a higher volume at a higher temperature, then your molarity is going to decrease a little bit. And here's an illustration of how to make a solution, a one molar sodium chloride solution. Molality is another term, very similar. Molarity versus molality, one letter different. The advantage of molality is that it is independent of temperature. The reason we have so many different quantitative descriptions for concentration is that each of them is more useful in certain situations than in other situations. So molality, not as useful necessarily in the chemistry lab when we're just doing regular stuff, but very useful in situations where temperature dependence is an issue. Here, this is the amount of solute in moles divided by the mass of the solvent, not the whole solution, just the solvent, in kilograms. The mass of solvent doesn't change with temperature, and so molality doesn't change with temperature. Parts by mass and parts by volume. These are used a lot. If you get the water quality statement from the city, it lists a lot of the potential contaminants in the water in terms of parts per million, things like that. That's generally a parts by mass. It's the ratio of the mass of solute to the mass of the solution multiplied by a factor. Mass of solute per mass of solution multiplied by a factor. The factor determines whether it's parts per million, parts per billion, etc. Percent by mass is the mass of solute over mass of solution times 100. So here the factor is 100. Percent means per 100. So percent by mass is really parts per 100. So this equation is useful. It's also useful to remember that 14% by mass means 14 grams of solute per 100 grams of solution. And that makes a great conversion factor. Parts per million, often abbreviated ppm. This is mass of solute over mass of solution times a million, 10 to the 6. Parts per billion. The multiplying factor is a billion, 10 to the 9th. So if we see a concentration that's 15 parts per billion by mass, that means 15 grams of solute per billion grams of solution. You can actually use any mass unit you want. You could use pounds here if you wanted, or kilograms, or micrograms, or anything, as long as the unit in the numerator and the denominator agree. Parts by volume follows the same pattern, but now we're looking at volumes of solute and volume of solution. So 22% ethanol by volume means 22 milliliters of ethanol per 100 milliliters of solution. This is typically used for things where the solute is a liquid. And then there's also a mass volume parts, but we won't go into that. Okay, so let's do a problem. What mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. Problems like this end up being dimensional analysis problems. It's just a matter of unit conversions. So let's write down what we know. We have 355 milliliters. The 12 ounces there is just to give you a point of reference. It's a 12-ounce can of soda. We have 11.5% by mass. That means 11.5 grams of sucrose per how many grams of solution? 100. Percent means per 100. Per 100 grams of solution. This density, that's 104 grams of solution per milliliter of solution. So we've got this density, which is grams per milliliter. We've got this, which is grams per gram. And then we've got this 355 milliliters, just a single unit. Without really thinking too hard about it or understanding too deeply, our best guess is that this is the number we want to start with, and we want to utilize these as conversion factors. The 355 cannot be used as a conversion factor. It's just not going to work. So we're going to start with the 355 milliliters. And what am I trying to get to? Grams of sucrose, right? So I'm going to figure out my path, how I'm going to get there. And that's going to be based on available conversion factors. Well, I need to get rid of milliliters. Well, this density would allow me to convert to grams of solution. So I could go from milliliters to grams of solution. And then this percent is grams of sucrose per grams of solution, and so using that, I can go to grams of sucrose. See how that works? So 355 milliliters times grams of solution per milliliter of solution, and that was 1.04. And those guys cancel out. And then I want grams of sucrose on top and grams of solution on the bottom. So those units cancel out. And that's 11.5 over 100. So I've got 355 times 1.04 times 11.5 divided by 100. Looks like I should keep 3 sig figs for my final answer, so I'm going to get 42.5 grams. $42.5 grams of sugar in a can of soda. Yikes. Any questions? These are the sorts of calculations that can be useful in everyday life. Looking at a lot of these conversion factors you can get off of a package because all the nutritional information is on there. And so you can figure things out just by manipulating the units. Another one is mole fraction. Mole fraction is abbreviated with the Greek letter chi. So the mole fraction of solute gives the moles of solute divided by the total number of moles, which is moles of solute and moles of solvent. So we can look at it this way. Chi solute, the mole fraction of the solute, is the amount of solute in moles divided by the total amount of solute and solvent in moles, and is often used to indicate number of moles. So it's the moles of solute divided by the moles of solute plus the moles of solvent. And this is useful in certain equations. The mole percent, come on, pointer. Come on, there we go. Mole percent is just the mole fraction times 100. So we just take this fraction and make it into a percentage. Okay, so here's a fun problem. Solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each of these units. So molarity. What do we need for molarity? We need moles per liter. Moles of solute per liter of solution. Well, we're given grams of sucrose. We have to convert that to moles. So I'm going to do that up here. 50.4 grams of sucrose. We need the molar mass, which I don't trust my memory on this one. 12 times 12.01 plus 22 times 1.008 plus 11 times 16, 342.3. So 342.3 grams per mole. Oops. So 0.1473 moles. I'm indicating where my last significant digit is and then carrying 2 extra digits to avoid rounding errors. That is my moles of solute. So 0.1473 moles. And I need the volume of solution in liters. Well, it's 355 milliliters. I need to divide that by 1,000 to get liters, so that's 0.355 liters. And this gives me, this is a final answer, so I'm going to round to 3 sig figs here, 0.415 moles per liter. If I make a calculation error, please yell at me. Literally yell at me. That one should be fairly easy. We've done molarity for a while now. Mole fraction. So here we need the moles of solute. We also need the moles of solvent. So I need to do another calculation. I'm going to make some space up here. I have the moles of solute, but I need the moles of solvent. What's my solvent? You guys are so dead. Water. It's water. I feel like I'm talking to myself, which really isn't that strange. I talk to myself all the time, but it's weird to do it in front of a group of people. 0.332 kilograms of water. We need moles. So first we go to grams. So I've got kilograms down here, grams up there. But you know, some of you want to do that in your head, that's fine. And then we're going to use the molar mass of water to convert to moles. So I've got basically 332 divided by 18.016. 18.428 moles. That doesn't seem right somehow. But there, yeah, it is. So there it is. Okay, so that's my moles of solvent. So mole fraction is moles of sucrose over moles of sucrose plus moles of water. So I've got 0.14723 excuse me, moles on top. And I've got 0.14723 moles plus 18.428 moles on the bottom. So I'm coming up, that should have 3 sig figs as well. 7.93 times 10 to the minus 3. Anybody else get that? At least one other person did. What happened to the units? They canceled out. Mole plus mole is just moles. Mole divided by mole, poof, moles go away. Mole fraction is unitless. Okay, molality. Molality is a weird one. Moles of solute do you remember what it is? Kilograms of solvent. Not the whole solution, just the solvent. So we've got this information. Here's the moles of solute, 0.14723 moles divided by, there's our kilograms of water, 0.332 kilograms. 0.14723 divided by 0.332. So this is 0.443 moles per kilogram. Molality is abbreviated with a lowercase m, generally italicized, trying to distinguish it from m for meters. I'm not a fan of molality, but I understand that it's necessary sometimes. So there's the molality. Mole fraction. No, mole percent. I'm getting ahead of myself. The mole percent is the mole fraction times 100. We already did the mole fraction. So we're going to take the mole fraction from up here, 7.93 times 10 to the minus third, unitless, and we're going to multiply by 100. So we're going to get 7.93 times 10 to the minus 1%, or you might prefer to say 0.973%. And then they want percent by mass. Percent by mass would be grams of solute over grams of solution times 100. So we have grams of solute. It's 50.4 grams of sucrose. What's the mass of the whole solution? We have to add. It's the mass of the solute. It looks like an, come on. Oh, just start over. It's a funny looking 5. 50.4 grams, plus we need the mass of the water in grams. So that's 332 grams times 100. So 50.4 divided by the quantity, 50.4 plus 332 times 100, 13.2%. These are all numbers that describe the same solution. And the reason there are so many ways to describe it is that they are useful in different situations. Any questions? We need to be able to take one concentration unit and convert it to another. What's the molarity of a 10.5% by mass glucose solution? The density of the solution is given. Well, 10.5% by mass means 10.5 grams of glucose per 100 grams of solution. I want moles per liter. I'm going to have to convert both of these units. I need to convert grams to moles of glucose, and I need to convert grams of solution to milliliters and then liters of solution. I've got the density here, so I can do that. If you're not given a density for an aqueous solution, and it's not something that you can look up, then the safest thing is to assume that the density is 1. So I'm just going to take this 10.5 grams of glucose per 100 grams of solution, and I'm going to convert these one at a time. I like to start with the top. So I need grams of glucose in the bottom and moles of glucose on top. And those units will get taken care of. And then I'm converting on the bottom now. So grams of solution on the bottom, I need grams of solution on the top. I'm going from grams to milliliters, so I want milliliters on the bottom. And then I want liters on the bottom, so I'll put milliliters on the top. So these cancel, and these cancel. Get all the units in there first, and then stick numbers in. So this one's easy. Milli means 10 to the minus 3, so I put 10 to the minus 3 on the other side of the line from milli. This one's given to me 1.03 grams per milliliter. Grams per mole, I need the molar mass of glucose, 6 times 12.01 plus 12 times 1.008 plus 6 times 16, 180.16. 180.16. So then I've got 10.5 divided by 100 divided by 180.16 times 1.03 divided by 1 EE minus 3 equals 6.00 times 10 to the minus 7. Moles per liter, or 6.00 times 10 to the minus 7 molar. I'm going to check that. Seems kind of small. But then I am dividing by a lot of big numbers there. I did something wrong. It's not -7. It's -1. Or 0.600. Any questions? Always a good idea to do a calculation twice, because even if you think you knew what you were doing, sometimes you just make a mistake. Sometimes it's the calculator sabotaging your work. I pushed the button. The calculator didn't register it. No questions?